Welcome back. So let us continue the next topic. So now the topic which I am going to pick up is how to find torque on an electric dipole placed in a uniform electric field. Okay, so the topic is torque on an electric dipole placed in a uniform electric field. The topic is torque on an electric dipole placed in a uniform electric field. So for this, what we are going to do is we have to consider a dipole, say minus q and a plus q. Let the dipole be placed at point A and the B respectively. This is B. Okay. So since it is a dipole, it is separated by a distance 2a between them. This is A. Now this dipole minus q plus q is going to be placed in a uniform electric field. So this is plus q charge. Now this is going to place in a uniform electric field. So these lines which are drawing here represents the electric field lines. So these electric field lines are moving from left side to right side. So I will mark this electric field as E vector. So what's the meaning of electric field in this direction? That means this side is accumulated with positive charge and this side is accumulated with negative charges. Okay, so that is why electric field always move from positive to negative charge. Okay, so now let theta be the angle. Let theta be the angle at which the dipole is inclined in an electric field. So now let us see what happened when this kind of dipole is placed in a uniform electric field in this situation. Okay, so that is why what we are going to do is what happened. So that is obviously it is a torque. Okay, so we have to measure the value of the torque on this particular dipole placed in a uniform electric field. Okay, now consider a dipole. A dipole, electric dipole, electric dipole of length 2a and dipole moment P vector equals to magnitude q into 2a. So this is your dipole having the length 2a and the dipole moment is P vector. So this is the dipole moment direction P vector here. Okay, now let us see what happened. Now if this minus q charge, look at this, there is a minus q charge at A and there is a plus q charge at B. Now very simple, if suppose a charge q is placed in an electric field E, a charge q placed in an electric field E, then it experiences a force which is equal to q times E. Why? Because electric field is equal to force per unit charge. So the force on a charge placed in an electric field is q multiplied with E. So here what we get here, so the charge minus q is placed in a uniform electric field E, so this charge will experience a force. This is minus q charge and this is your A, position A. Now let us see the charge minus q. So this side is positive charge and this side is negative charge. So the minus q charge will be attracted towards a positive direction or positive side charge. So the force on this charge minus q will be F is equal to QE. F equals to QE. F equals to QE. So this is the magnitude of the force. If we find the direction, then as I have already said, it will be towards a positive charge. And if this is the direction of the electric flow, the force will be opposite. So in vector form, we will represent by F equals to QE, but here it represents the same direction, so I will make minus sign here. So this negative sign indicates that the direction of the force and the direction of the electric field are opposite to each other. Okay, now then this is a force. Another, look at this charge again, charge plus Q here at B. So this charge plus Q placed in the uniform electric field E, this also placed in the uniform electric field E, so this will also experience a force on it. So obviously the force is equal to multiplication of Q into E. The force is QE. But here what happened? So this is positive charge here in this side, and this is also positive charge here. So this positive charge will repel this positive charge. So the force is along the same direction to that of the electric field E. So I will mark this F1 and I will mark this as F2. Okay. Now we got two forces, F1 and F2. Okay. So we can also write force on the charge minus Q at A. Force on the charge minus Q at A, F1, I will mark this as F1 equals to minus QE. So this completely represents the force and the direction, okay, and the vector, okay, form. That is F1 equals to minus QE. Okay. Now again I will mark this as equation 1. Again, force on plus Q charge at B. Now let us see what's the force on plus Q charge at B, at this force. So I am just making this F2 equals to plus QE, equation number 2. Now you find that F1 and F2 are equal in magnitude. Though they are different in direction, they are equal in magnitude. Okay, so now, so the system, the whole system is now under the effect of two equal and opposite forces. Under the effect of, listen, under the effect of two equal and opposite forces, but these two forces are acting along two different lines. Say for example, this is the example of the dipole here, and it is placed in a uniform electric field. So consider this the length of the dipole. Now here the force F1 is represented by this term along this direction, and F2 is represented by this finger. Now let us see what happens if these two forces are acting. Now look at this. Look at the pen. Look at this pen. It was like this. So if they pull, so it is moving. Moving in what direction? Moving in a turning movement. Okay, and this turning movement of force is what we call as torque. So that is why the two equal and opposite forces acting along two different lines constitute a torque, and that torque is to be measured. Okay, so thus the dipole is under the effect of two equal and opposite forces. Thus, the dipole is under the effect of two equal and opposite forces, which constitute a torque. Now, this dipole constitutes a torque, and the magnitude of torque is given by, now we will measure the magnitude of the torque. Now the magnitude of the torque is given by the torque tau is equal to magnitude of This is what we have studied in class 11, how to measure the torque. Torque is the actual vector quantity. The magnitude of torque can be measured as magnitude of either force, any one of these two, into magnitude of either force into perpendicular distance. Perpendicular distance between whom? Between the two forces. Between the two forces. So the torque is the magnitude of multiplication or product of the magnitude of either force and the perpendicular distance between them. So this is the torque tau is equal to magnitude of, I will pick up the magnitude of any of them, that is Q into E, and multiply with the perpendicular distance between them. So it is B multiplied with Bn. So let us see what is Bn here. Okay, so but I am not writing Bn here. So let us continue this triangle. Let us see what is the perpendicular distance between these two forces. Now, which one will be perpendicular distance? So now we have F2 here and now we have F1 here. Perpendicular distance between the two forces. This will be the perpendicular distance, 90-degree perpendicular drop from F2 to F1. So that is why obviously this Bn represents the perpendicular distance between the two forces. So here I will write this as Bn. How comes Bn? And this is the distance between F2 and the F1, perpendicular. Okay, so now this is Bn. So the torque tau is equal to QE. Now what's the value of Bn? So now Bn is your opposite side. This is theta. Look at the triangle. A and B, right angle triangle. So this is your 90-degree here. So this opposite side is equal to, the component opposite side is equal to 2a sine theta. So since Bn is 2a sine of theta, let us see what happened here. Let us continue here. So the torque tau is equal to QE. Now look at this, Q, charge, and 2a. So what is Q into 2a? Q into 2a is what we call as the magnitude of the dipole moment, Q into 2a. So I should represent this P for Q into 2a. So P E sine theta. So this is the magnitude of the torque. This is the magnitude of the torque on this electric dipole placed in the electric field. Now this is equation number 3. Question number 3. Now in vector form we can write. Now that is, how can we represent this? Because torque is a vector, and how we can represent this in the vector form. So the torque tau is equal to vector is equal to P E sine theta is P vector equals E vector. So this is the representation of the torque in the vector form. Okay, so this is vector form. This is the magnitude, how to measure the torque. Okay, so now let us see. So very simple. Let us consider now recap. Let us consider a dipole placed in a uniform electric field making an angle theta. Now let us see. F1 is a force and F1 equals to Q times C, because this force is multiplication of the charge and the electric field, and now the force F2 is QE. So these are question number 1 and 2. So these two forces constitute a torque, and that torque is torque equals to magnitude of either force into perpendicular distance between the two forces, and now we get the torque as P sine theta, or torque equals to torque vector equals to P vector cross E vector. Okay, now case 1. Let me consider some cases. If theta is 0, theta is 0. Theta 0 means what? If this is theta, I am keeping like this. Okay, that means I am keeping the dipole along the direction of electric field. Okay, so if theta is 0, so sine of 0 degree equals to 0. So what's the torque? Torque is 0, and this is the minimum torque. The minimum torque is obtained at what? At theta equals to 0 degree, and if we keep the dipole moment P in the same direction to that of the E. Okay, and case number 2. Case number 2, if theta equals to 90 degree, sine of 90 degree equals to 1. Let us see, if I keep this theta perpendicular like this, if I keep the dipole like this, then look at this pole here and this pole here. Okay, so it also constitutes a torque, and what should be the value of torque in this case? So it is the torque tau equals to PE, and this is the maximum torque. Maximum torque. Okay, now these are the two cases, case 1 and case 2. Okay, so that means in the case number 1, what you have, if you keep the theta here 0 degree, that means the dipole is in the stable equilibrium. Stable. No forces, no torque. Okay, no torque, no force, because the two forces cancel out, and now the torque is again 0. Okay, so it is called stable equilibrium. Okay, and it is a maximum. Now one more case, if I keep the theta at 180, P is different. If I turn this plus Q here and the minus Q here, and it is kept in the direction of electric flow here. That is the direction of electric flow. And now this is P, and it is opposite to the direction of E. What will happen in this case? Okay, so in this case, so if it is plus and plus cannot stable. Okay, and minus is also not stable. Okay, so that means if I keep the dipole at an angle of 180 degree, that means the direction of the P is opposite, the dipole moment is opposite to that of the electric field, then what will happen? The torque will rotate at an angle of 180 degree. 180. That means it will try to come to the original stable equilibrium. Okay, so that is why 180 degree is unstable equilibrium. So theta equals to 0 degree, stable equilibrium, and theta equals to 180 degree, unstable equilibrium. Okay, so this is what we have studied for the dipole. So this is a part of your syllabus, so you have to practice it, you have to note it down, you have to copy it down. Okay, and we will be back, okay, with some more numerical problems related to how to measure the electric field, okay, of certain system, okay, and how to measure the dipole. Okay, that is the electric field due to a dipole. Okay, thank you. We'll be back again.